I'll begin. Dear Father, we thank you for this day. Again, Lord, I thank you for the opportunity you have just to meet together and talk about you freely here. Just pray that you bless this class, Lord. Help us to glorify you in what we do, Lord, this day. In your name I pray. Amen. Oh, okay. It's just you never know around here when construction is starting, so I'm always a little bit weary. Okay, so I hope you enjoyed the video. It didn't overlap much with what I'd already said, but it did a little bit, which has cost me some time effectively. We'll see where we get to today. So, I do intend to give you an example of Cauchy's theorem. Excuse me, Cauchy's theorem, Cayley's theorem tomorrow in the help session. I'll try to give you an explicit example of that. Let's see here, some of you started. These pages, my pages have gotten out of order here somehow. So, a few more things to tell you about isomorphism and homomorphism. So, just to recap, if we can find a mapping phi, right, which goes from say G1 with some operation star to another thing, say G2 with operation number sign. If you thought that's hashtag, you're wrong. No hashtags in my class. Then if this, if we have phi of A star B equals to phi of A number, I guess we used to say pound, didn't we? For all A and B in G1, then of course phi is called a homomorphism, right, of G1 and G2. And then if, in addition, if we also tack on to this, what additional feature? If it's a bijection, then what do we get? Then what happens? If we got a bijection, which is also a homomorphism, then what? Right, phi and isomorphism, and then what do we say? Right, G1 equals squiggly G2, aka G1 and G2 are isomorphic. Now, I think I said something incorrect, like the day before last. I said that if there was a homomorphism from G1 to G2, that they were homomorphic. I don't think that's quite accurate. I would prefer to reserve that terminology. That, and all of my examples were like this. So if you have phi from G1 to G2 and onto map, onto homomorphism, then you could say that G2, which by the way would be equal to phi of G1, is homomorphic. G2 would be homomorphic to G1. Although if you look, you don't see that language much, maybe not at all in the book, right? So isomorphic you see, homomorphic not so much. My point being that, if you have a mapping from here to here and it's not a surjection, it doesn't really say much about G2. Whatever doesn't get hit in G2 doesn't really have anything to do with G1 per se. So that's probably not a good term that I threw out there before. Okay, so theorem. We run through some theorems that I should really make sure that I tell you. Notes keep getting out of order here. Theorem. If we have alpha from G to H, a homomorphism, all right, and if G and G has finite order, then the order of the image of G divides the order of G. Okay. I may have said this before, but I certainly should repeat it. It's worth repeating. So here's the proof. It's very simple. Let's see here. So to say G has finite order means what? Right, G to the n is equal to 1, let's say. Right, for some natural number, right? Right. Then if you look at alpha of G raised to the n power, what do you get? You get alpha of G to the n by the laws of exponents property for, I mean, this we proved day 1 for homomorphism, right? That we could pass powers into and out of homomorphisms, right? And so, of course, this is alpha of 1, which we also proved maps to 1 for a homomorphism, right? Day 1, we did prove that already. Well, so what's it say? It says that this element, alpha of G, raised to the n power is equal to 1. So that implies that the order of alpha of G has to divide n, right? We have this theorem. If we have some element to the power k, how does k relate to the order of the element? Well, it has to divide it, right? In other words, if you have some element raised to a power getting the identity, that power must be a multiple of the order of the element. So there it is. Now, what's a more useful theorem? And this is kind of also, well, sometimes it's useful, like sort of, this is sometimes more useful in disproving something than proving something, okay? But a theorem, if alpha from G to H is isomorphism, right? Then the order of alpha of G is equal to the order of G for all G and G. In other words, isomorphisms preserve order. All right? Let's look at the proof in the finite case. All right? Right, so let's see here. If we have the G to the n is equal to 1, right? And alpha is, isomorphism, what's that mean? Well, let me get back to that in just a second here, but let's just suppose alpha is an isomorphism as advertised. We have alpha of G to the n is what? Alpha of G to the n, which means that's alpha of 1, which is 1, because it's 1 maps to 1 under homomorphism, right?
Can we just take the above theorem and then apply it in both directions since it's bijection, so it's inverse is also homomorphic?
Perhaps. Let's see here. Then alpha of G. So what does this give us here so far? Right? The order of alpha of G divides n, right? What we want to show is what?
There's nothing less than n.
Right. Something I was going to...
You could work that in reverse, couldn't you? Just say, like, suppose there's some k less than n, such that alpha of G to the k equals 1, and then wrap it back in, and then you'd show that you'd have G to the k equals 1.
So I think...
So
let's see here. The argument that Sam wants me to make is that alpha inverse is also an isomorphism because the inverse of a bijection is a bijection, and we have that theorem from the book, although I haven't proved it in class necessarily, all the bits and pieces, but it's in Nicholson. So alpha inverse is an isomorphism. So from that, see, but then how do you apply that to this data? Order of what?
The order of G divides the order of alpha G, and the order of alpha G divides the order of G.
that's what I'd like, but my question specifically is how, like which map am I using this theorem on? Alpha inverse, right? From H to G, right?
So you get,
Which I should apply this theorem to what element to get data?
so you apply that, you say order of alpha inverse of alpha of G equals order, it divides.
The order of alpha inverse of alpha of G, right?
Divides order of alpha G.
Has to do, see, I'm sorry, I'm using my bars here. Let me make this divides the order, what'd you say?
Order of alpha G.
Order of alpha G. Right, and this is equal to what?
Order of G.
Right, this is exactly the order of G. So we have the alpha of G divides n. In other words, we have divisibility both ways, which means we have equality, right? So this is, I mean, in other words, this is order of alpha of G divides n, and n divides the order of alpha of G. Now, the thing I don't like about this proof, and I'm not saying I don't like the proof, it's not bad. The gap for me lecture-wise is that I haven't proved that alpha inverse is an isomorphism when alpha is an isomorphism, have I?
So should we prove that?
I think you sketched the proof of it.
Oh, I sketched the proof, okay. I'm sorry, my memory of what we've done in here or not, it's not optimal. So you guys remember better than I do, but that's a decent proof. The other proof, which you were starting to get me at, wanting me to scratch at, would be like contradiction or something, perhaps. So you could have supposed that, you know, suppose you had G to the J. Oh, curses. Well, the other proof would be basically by, let's see here. The other path to go down here, if we don't take Sam's advice, would be, I'm trying to show what? The order of, I want to show that the order, so we have that the order of alpha of G is less than or equal to n by this, right? Is that wrong?
You come up with some J less than n and basically try and say that.
Is this right first, though? Am I wrong? Is that what this red argument proves?
Should be, because it wouldn't divide n if it's larger than n.
Right. So we suppose that alpha of G to the J power is equal to 1 for some J less than n towards a contradiction and see if we can find one, right? It's pretty easy to find that contradiction because this would be alpha of G to the J, right, equals to 1. But this is also equal to alpha of 1, right, which implies that G to the J is equal to 1 by 1-to-1 alpha, right, using injectivity of alpha. But then that implies that the order of G is less than J, which is less than n, or doesn't equal to J, which is less than n, which of course is a contradiction to the fact that we assume the order of G was n. So also a good argument. We go either way.
So then given this, if we know that the order of G is finite, this shows to be an order of alpha and vice versa, which gives us automatically the contrapositive of that, which is that if one of them is infinite, then the other must be infinite.
Ah, very good. So we get the infinite case by the contrapositive. I like that, yeah. But this is super useful, right? Because if you have two groups, right, and one of them has an element of order 5 and the other one doesn't, they're not isomorphic. That's what this theorem is useful for, right? If we look at two groups and they have different, you know, if there's an element of order whatever that's not in the other one, then you can be sure they're not isomorphic. They don't have the same structure as a group. It's a very, very useful observation at times. Okay. This theorem's super easy, but worth talking about. Theorem, we have alpha going from G to H, and onto homomorphism. So you might say it's a surjective homomorphism, okay? Then, number 1, G abelian implies H abelian. And number 2, G cyclic implies H is cyclic. This theorem is a joy to prove. Makes an awesome test question, right? So here's the proof. let, assume alpha from G to H is, surjective homomorphism. Sorry, I keep repeating myself. Okay, let's let x and y be elements of H, right? H is equal to phi of G, right? Oh, I'm sorry, phi, listen to me. Alpha, currently alpha of G, which implies that there exists A and B in G such that what? This is in fact nothing to sneeze at. Oh, I keep drifting back into, I really want to make it, I keep changing alpha to phi for some reason. I have no good explanation for that, but alpha of A could be X, alpha of B can be Y. I'm sure that I can find these because it's onto. That's the definition of onto, which you know from your previous coursework. Hooray. Okay, so you take X, Y, which are just two random elements in H. That's actually equal to alpha of A, alpha of B, right? Homomorphism property, that's alpha of AB, right? And that is alpha of BA because why? AB equals to BA for all AB in G, because G is abelian by assumption, right? I should really just, for every proof I do in class, at the start, just say, assume the the preconditions of the theorem and stop writing stuff over again. Because I always only write half of what I need to write, right? So, anyway, sorry about that. Now, alpha is a homomorphism, right? So this is alpha of B, alpha of A, which is, of course, y times x. So this implies that H is abelian because we just showed that any two elements, arbitrary elements, commute with one another. The proof of 2, much the same. Assume the conditions for 2, okay? Assume G cyclic. Let's assume that G is equal to, suppose G is generated by A, right? Let X be an element of H, right? Then X is equal to alpha of something, let's say G, right? For some G and where? For some G and G. But G is an element of a cyclic group, right? G is equal to A to the power K for some, some K in the in the integers, right? So check it out. X equals to alpha of G, which is alpha of A to the K, right? Again, the law of exponents, we proved the fact we proved laws of exponents sort of filter through homomorphisms in day one. That's so important to everything we do. We can pull the K out, right? Aha! Well, this is an element of this guy. See, because that's generated, that's in the subgroup, cyclic subgroup generated by alpha of A, which of course is a subset of what? Right? So we have that, what I'm arguing is, I'm actually making a comment here. Is this clear that this is a subset of H? Why is this a subset of the H? What is H? H is a group. What is a cyclic? We've proved before that a cyclic, that this generator, right, that alpha of A, to the power K, this is going to be a subset of a group. Pick any element of a group, right? The cyclic subgroup generated by that element is a subset of said group. So this inclusion is clear. This argument right here, though, we just picked X, an arbitrary element of H. What's this argument show? The reverse inclusion, right? This right here shows that X is an element of this guy. And that implies, and of course, X is an element of H, right? And we just showed that that implies, X element of H. We just showed X element of H implies that X is an element of the cyclic subgroup. We have, of course, then H is a subset of this guy. So we have double containment. So consequently, we have, so it's stronger than just what I said, right? yeah, the homomorphic image of a cyclic group is cyclic, but it's better than just that. Not only is it cyclic, it's generated by the image of the generator under the homomorphism. It's really nice. Right? So this theorem, actually, the proof shows you something stronger, right? Which is that G is equal to A, and H is equal to the cyclic subgroup generated by alpha of A. That's what the proof showed us. Any questions? So he has, Nicholson has his theorem 2 in this section extends this idea to groups which are generated by more than one element, right? And he basically has, he says, okay, so you take two homomorphisms. Let me just talk about his theorem 2. I'm not going to prove it. I just want to talk about it for a second here. What he does is he studies alpha from G to H and beta from G to H. He tells us that both of these are homomorphisms, right? Homomorphisms. And he says that G is equal to it's generated by X. So here, X is some subset of G. It's called a generating set. So for example, we looked at this a few lectures ago. We showed that like S3 can be built from a generating set with 2 elements, right? But this idea extends. You could look at generating sets with, that's annoying, more elements, and then you just take all possible products of all possible finite products of all possible integer powers, and this gives us the subgroup. This gives us, if that generates the group, then X is said to be a generating set for the group, right? And what he proves in theorem 2 is that if you have basically alpha restricted to X equal to beta restricted at X, that's true if and only if alpha equals to beta. So this theorem 2 is the group theoretic analog of the theorem we have in linear algebra that you can prove 2 linear transformations are equal if they're equal on a basis, right? So basis is a generating set for a vector space, much the same. You can say something stronger here, though. You see, if you have a generating set, right? If you have a generating set for a group, you can define a homomorphism by just sending the generators someplace in the other group, possibly. There's something you could say, like if you could build a homomorphism from just acting on generators. There's a better version of theorem 2 that could be found. I just want to say that. I don't have time today to try to flesh that out, but homework maybe. Maybe not. I already assigned your homework, didn't I? All right, let me stop blathering about that and do something more precise here. This is example 14 from Nicholson, which is an important example for us to talk about. And this example might possibly be helpful with the most difficult problem in your homework, which is what? No? You being good 421 students have already started working on this homework, right? Okay. I believe that. I believe it. I think it's true. This is example 14 from Nicholson. That problem about the rational numbers and a proper subgroup of the rational numbers, to me, that's the most difficult homework problem. That one required some, am I using this in here? In my notation, I'm a little bit, I can't remember. Anyway, for this, I mean non-zero, all right, rationals. The non-zero rationals under multiplication form a group, of course. And example 14 is to show that these are not not isomorphic. All right. So I'll show you the argument he gives us. It's pretty simple. It's pretty simple if somebody else tells it to you. Okay? but finding it, I don't know, maybe it's the thing, what's the thing that typically fail? I mean, the thing we spend a lot of, maybe too much time in Math 200 on is, you know, square root of 2 is not a rational number, right? I'm sure everyone here has seen that, right? And been tested on it more than you'd like, perhaps, I don't know. But this is basically just built off that idea. So we assume that we've got sigma from the rationals under addition to the rationals, non-zero rationals under multiplication, right? An isomorphism. And we're going to prove that that produces a contradiction. All right, so the next thing is, you're like, okay, well, there has to exist some q, right? Some rational number such that sigma of q is equal to 2. That, so far so good, seems reasonable, right? Okay. Then he's like, suppose that sigma of 1/2 q is equal to a. Now this a is going to be the troublemaker, right? We look at a squared. A squared is sigma of 1/2 q, sigma of 1/2 q, but then, let's see here. We're talking about an isomorphism, right? From where? From the additive to the multiplicative, right? Remember that table in the video you guys watched? I'm sure all of you watched it. I watched it at double speed. I thought it was kind of slow. It's like, you got stuff to cover. Stop spending so much time. Anyway, so the point is that this is 1/2 q plus 1/2 q because of the definition of isomorphism between additive and multiplicative. And that, of course, is q. Uh-oh. So that's sigma of q, which we know is, by construction, 2. So apparently, a squared equals to 2 has solution in the rationals. This is a contradiction, right? There's no square root of 2 in the rational numbers. So that implies sigma does not exist. There is no isomorphism. That's the argument. Kind of, this example, I think, flexes a sort of different muscle than our other examples, doesn't it? Yeah. Or set of muscles. Maybe a third arm we didn't know we had. I don't know. Something. Any questions? No? All right, if I can find my next example for us, get into that. One of the things I should say, if I can ever find my stuff, there's a theorem which is missing from Nicholson, which is really a very useful theorem for isomorphisms, and I think you guys should have it to work with because it is extremely useful. So let me state it. This is from my notes from last year, which of course are based on the classic text by Galilean, which is both better than worse than our current textbook. I mean, you know, like every textbook has its strength, has its weakness. Let's see here. But here's the theorem. This is my theorem 2.27 from my 2016 notes. All right. And the theorem simply says this. If G and H are groups, all right, and we have phi going from G to H, an isomorphism, then if, that's the data, if B is an element of G and K is an element of the integers, then the equation x to the power k equals to b, all right, has the same number of solutions in G, as does y to the k equal to phi of b in H. Here x is an element of G, whereas y is an element of H. Since equations are easier to think about than other things sometimes, this is an extremely useful theorem just for intuitive purposes, right? So like here's the proof. Let everything be as in the statement of the theorem. Suppose, excuse me, x to the k equals to b, right? Then what can we say about phi of x to the k? Equal to phi of, phi of, well, this is equal to phi of b, right? Which says what? Phi of x to the k, right, is equal to phi of b. What does that say? Lower. Before that. What does it say about phi of x is in H, right? Phi of x is an element of H. And if we say y equals to phi of x, then what? Y to the k is equal to, what I'm trying to say is this is a solution to the equation. And now you're going to argue, not only is it a solution, how many such y's are there? Same number of the x's, because phi is a bijection, right? So if the solution set has three things in it, right? Then we feed those three things to a bijection. How many things do we get on the other side? We get three things, right? Bijections are bijective correspondences, right? That's the first thing we learn in Math 200 in that regard. That's pretty much the proof. Okay, so.
So they're not only the same number of solutions, they're the same solutions under the bijection.
Yes, that's true. Not only are they solution sets, they have to be transferred naturally under the bijection. That's true. Well, where this is useful is not so much in constructing isomorphisms, it's in denying the existence of isomorphisms. For example, if we look at G equal to the non-zero reals, right? I guess, am I using R star for that this semester? I forgot. Anyway, and if we look at H equal to 0 to infinity, right? So both multiplicative. Multiplicative. I can't spell. There we go. Saved. What example was I on? I don't know. Example. I give up. I was on example 14 earlier, but that's from the book. So my organization is waning. So here's the point. In G, right, what do we have? X squared equals to 1 has what? First of all, 1 is super useful, right? Because if there is an isomorphism, what's phi of 1 have to be? Phi of 1 is 1 again, right? So if you study the units, I'm sorry, that's not the way to say it. Here I'm studying idempotence, I suppose, but what are the solutions to the first one?
1 and minus 1.
1 and minus 1, right? Solution set. This one has solution set what? Just y equals 1 as solution, right? So this equation, x squared equal to 1, has a different number of solutions for the non-zero multiplicative real numbers and for the positive real numbers. Therefore, these are not isomorphic as groups.
Doesn't this just prove that there can't exist an isomorphism in the sense 1 to 1?
Isomorphisms automatically send to 1-to-1. Every isomorphism sends 1-to-1 because every isomorphism is a homomorphism, and homomorphisms send 1-to-1. That's fine. It's a good question.
So we really want to look at one is the most useful thing to use for this, because otherwise they could be different elements.
Yeah, that's true. But I mean, if you're I mean, there could be other. So here's another one. If you look at x to the 4th equals to 1, right, then we have x equals to plus or minus 1 in non-zero reals, right? But on the other hand, y to the 4th equals to 1 means that y is plus or minus 1 or plus or minus I, right, for non-zero complex numbers under multiplication. And this gives us a nice proof that there does not exist an isomorphism of the non-zero complex numbers and the non-zero real numbers. This is a much harder thing to prove without this theorem. Not impossible, but you'd actually have to kind of pick at I mean, basically a proof otherwise would have to be centered around the fact that there's an element I in the imaginary numbers, which is not in the real numbers, and getting some kind of contradiction from the fact that there's this object in the complex numbers, which is not in the real numbers. Your proof would have to be centered around that. With this theorem, it's just easy as looking at equations and going 2 solutions, 4 solutions, so they're not, it's not isomorphic. I shouldn't even show you this. It makes it too easy. I really shouldn't show you this. I mean, this over here, I mean, maybe you could go back and do this example over with the theorem, right? So, all right, with that, I shut up about that. That is something missing from Nicholson, I just noticed. But it's important, so we should talk about it. Finally, let's get back to isomorphisms. Well, get back to it. I guess we never left it. So we've been talking about, how to compare 2 groups and the structure of 2 groups with the existence or non-existence of an isomorphism, of a homomorphism, right, which is a bijection. But another thing we should do, and in fact is important, really important, in fact, is to study isomorphisms on their own right. So if we just look at the set of isomorphisms, as the composite of an isomorphism and isomorphism. Let me be more specific here. Give you some definitions. Definition. Ought. So what this is sigma from G to G, such that sigma is isomorphism. It's understood that G has the same operation in the domain and the target. So an isomorphism from a group to itself is called an automorphism. The set of all of these is called the automorphism group. These are automorphisms of G. Auto meaning self, morphism, well, you got it. So these are self-morphisms of G, automorphisms. G. You can also talk about the so-called inner automorphisms in G. This is sigma sub G, such that G goes to G again. And sigma sub G of x is conjugation by G. Gx, G inverse like this. These are the so-called inner automorphisms. Now, I don't think I've proved it in here, but as I'm often known to say, these would make nice test questions. Sorry. There's a theorem. This actually not any part of this theorem we could prove. It wouldn't be that hard. The inner automorphisms of G are in fact a subgroup of the automorphisms of G, and those are in fact a subgroup of the permutations of G. What was permutations of G defined to be? Yeah, bijections. Here, it's the function space from G to G with operation of composition. Right, right, which makes them special. At the end of the last video lecture, we looked at a lot of things that were permutations, but might not have been. So, like something that's in here, but maybe not in here, would be something like left multiplication by G, right? This mapping, left multiplication by G, is probably not an automorphism, and yet it's a permutation on G. So the left multiplication maps are in the permutations. The left multiplication by the identity, of course, is in here. The left multiplication by identity is the identity map, right? And then still more special are the automorphisms which are produced by conjugation by a particular element. You can prove all of these by the subgroup test, right? This being a chapter 0 thing, right? That the composition of bijections is a bijection, and the inverse of bijection is a bijection, and they're associative, and the identity map's in there. So that gives us the permutation on the group is a group. And then below, we can just use subspace test, the subgroup test. But I think what might be more interesting for you guys than me going through, those are routine. Everything I just said is pretty routine. What's probably more instructive for you guys is if I look at a specific example and try to investigate what are the inner automorphisms of something in particular and see if we can't understand it. The calculation required for this example is actually instructive as well. It kind of scratches an itch, which I haven't scratched too much in here, but is scratched in Nicholson if you read the section on isomorphisms. This is my example 2.2.13 from my 2016 notes, all right, which is on page 70, perhaps, unless I don't know. Sometimes I edit things. But anyway, so we're going to look at automorphisms. We want to look at the automorphisms of Z3, all right, where Z3, of course, is 0, 1, and 2, so that's an additive group. Goodness gracious. So something I have not said today yet, but I think is right on the surface of things, which is that isomorphisms have to map generators to generators, right? I'm not sure. I think I've almost said that if I haven't said it exactly, but it is nonetheless true. So let us move forward in light of the truth of this. What are the generators of Z3? 1 and also 2, right? So the question that I want to ask is, what are potential isomorphisms from Z3 to Z3, right? In other words, can we what are the automorphisms from Z3 to itself? Okay, so alpha 1 has to map 1 to somewhere, right? If alpha 1 goes to, alpha 1 can go to 1, right? That's one possibility. What's the other possibility? The other second possibility, alpha 1 could be 2. Is there anything else you could do with that generator? I mean, that's it, right? And if you look at, if you consider the other generator 2, you'll actually produce the same maps. It suffices to look at what happens to one generator as it goes to all other possible generators, in this case at least. So let's see here. Excuse me. So alpha 1 of, goodness gracious, I'm trying to think of the words here. Alpha 1 of, if we do that, what's the formula for n times 1? This is n times alpha 1 of 1, right, by laws of exponents and additive notation, which in other words says that alpha of n is equal to, so what does this mean? Alpha 1 is actually the identity map, right, on Z3. Adios, el presidente. So you could call that 1 if you wanted to confuse the students. I'm not attempting that today. Alpha 2 of, I mean, basically, we already know what happens to 1. What happens when we look at alpha 2 of 2? We just go, this would be what? This is alpha 2 of 1 plus 1, which is what?
Alpha 2 of 1 is alpha 2 of 1.
Right. Anyway, so that's apparently 2 plus 2, which is 1 again, right? We're in Z3. I feel like I'm not getting to the point here rather quickly, rather efficiently. So my question for you guys is, well, oh, here's a better calculation. This much we could, what's alpha 2 composed with alpha 2 of k? What's that equal to? This is alpha 2 of 2k, right? Which is equal to 2 times 2k, right? Which is otherwise known as k, because we're in Z3, right? But this calculation holds for all k. So what's that tell you about alpha 2 composed with alpha 2? Right? So if you believe me, right, about your future test question, that the set of automorphisms forms a group, right, then this should be a group, right? What's the group we're looking at? We got the identity, and we got this alpha 2. What's its multiplication table? I'll do the easy one. Wait a minute, there are only easy ones here. So, I mean, alpha 1, right? So what is the automorphisms? So we can see from this that the automorphisms of Z3 are apparently isomorphic to what?
Z2.
Okay, Z2, or C2. I was looking for Z3 star, but yeah. In fact, this is not an accident. It's not that hard to prove that this generalizes. You can prove that the automorphisms of Zn are isomorphic to the group of units under Zn. The essential idea of the proof is that you can define alpha sub j of k equal to jk for each j in Zn star. And that defines an isomorphism. What are the generators? And if you think about it, that's all the possible automorphisms, right? Because in order to create an automorphism of Zn, you have to send generators. What are the generators of Zn? They're the elements that are relatively prime to n, right? They're the things in Zn star. And so I think, you know, if you look at this, if you take alpha sub j1, alpha j2 of k, what do you get? you get alpha J1, J2K, right, which is J1, J2, K. So that's alpha J1, J2, K for all K, right? I'm sorry, that's for alpha and Zn. J1 and J2 are in star. So you can start to see how the mapping is just this, like phi from Zn star to the automorphisms of Zn. You can define the isomorphism of these two things by phi of j just equal to this alpha sub j. That's actually explicitly the isomorphism from the group of units mod n to automorphisms of Zn. Now, there's a lot of details here. Of course, I've left out. Many of those details are found on page 71 of my 2016 notes. But well, guys, we have a test coming up, as you know. Your homework is due Friday. I think I'm not going to test on 2.7, so we'll test on up through isomorphisms, but we won't test on groups of symmetry groups just yet. Okay. And I know I think there's like a token, maybe 2 problems in the training mission on that. So you can just push those to the next one. You can skip them. Okay. Make sense?